Good afternoon, everyone. Today we are going to talk about challenge 3, the Damn Vulnerable DeFi series. So in this challenge, we are talking about a flash loan pool which holds 1 million DVT tokens. On the other hand, you have nothing. So in this challenge, what you are going to do is you are going to take all the tokens from the pool. And you should try to do it in one transaction, okay? So let's look at a contract. Actually, there are only one file over here, so it's extremely simple. First of all, we are using two other facility. One is called address.so, which I'm going to explain. The other is called reentrancyguard.so. So these two are actually from OpenZeppelin, so they are kind of like standard library. It should be no problem. So the problem should not be there, but should be really in this file. So we are using the address library, and then so the whole thing is on this function. Okay, so one of these line is a problem. So flash loan takes 4 arguments. The first one is how much you are going to borrow. The second one is who is the borrower, the address. The third one is the target, which is expecting provided by the borrower. It's a contract address provided by the borrower, and expecting this contract, whatever contract you provide the client, is going to return the money. And then the last one is call data, which is low-level function call encoded arguments. So as you expected, there's actually two lines, line 29 and line 2034, trying to protect stealers, trying to protect nobody's going to steal money. So we check the balance over here before we make the loan, and then we send the amount here to the borrower. And then the line 32 is supposed to be, well, I use the word supposed to be, but so you can imagine the argument is arbitrary address and the function call is a low-level call, which basically allows you to call any function in the target address. So sounds a little bit dangerous there, right? So and then, but the protection is also here either. So theoretically, regardless what you do over here, I'm going to check my balance again. So if you do bad thing over here, if I check the balance, if it's smaller than this, I'm going to revert. So it's a little bit tricky because I already have a protection, and if these condition 34 fail, we are going to revert. So how can attackers steal money from here when you have such a strong protection at line 34? Okay. In order to understand that, we need to understand two things. Number one is we call reentrancy guard. Okay. And this guard is used a lot in contract because people might be able to for example, do a reentrancy attack. For example, one of the things you can do over here, if without this protection, is when you call a function call over here, you can call back to either the same function flash from or another function in this contract, and that is very dangerous. And a lot of reentrancy attack happen in that way. In other words, you call the target and target call you back. Okay. However, because of reentrancy guard we put over here, that becomes impossible. So we put this so-called modifier non-reentrant over here. It's impossible, and let's see why that's impossible. Because that's protected by the reentrancy guard also. So let's look at what this file looks like. Okay. So as you can see, the trick is we have a Boolean variable over here called entered or not entered. Okay, so either not entered or entered. So these two constants, we are changing this status to be either 1 or 2. Okay, initially it's not entered, so initially it's 1. So you use the modifiers, say non-reagent. So basically you do two things. In the beginning of the function, so the modifier usually is a pattern. So this underscore means the body of the function that apply this modifier. So this means in the beginning of the body, we do non-reagent before, which is going to change it to enter. On the other hand, after we exit from the body of the transaction, we are going to do this, which means we are going to change it to non-entered. So if I add this modifier non-reagent to the flash long function, that means before this whole body, this non-reagent is going to change status equal to enter. On the other hand, when the whole body is finished, the same modifier non-reagent is going to be changing the status to be non-entered. So because of this, nobody can enter into the flash long twice. Okay, so in other words, you cannot have two instances of flash long running, because if the second one trying to run flash long, you have this check over here. So you are going to do the first non-reagent before, which is going to check it's not entered. So it's already entered. You cannot enter again. So immediately it's going to prevent the second entrance. And that's how it's protecting the entrance attack in real life. So in other words, for this particular challenge, non-reentrance attack is impossible, at least not for professional. So you cannot enter this. And that's the only function over here, so we cannot call any other function either. Okay? So we need to think about something else, and that something else has something to do with the other library called address. Okay, and of course, address.so itself has no issue, but we need to understand how it works. So basically, address.so allows us to do a lot of low-level function call, which calls arbitrary function from another contract. So let's look at this. The first one is if you give me the address of the contract, I'm able to decide if that address is actually contract or not. Because we also have a so-called EOA, means you know means it's just a wallet address, it's not a contract. So if that's the case, then the code length is going to be 0 if there's no code. So by this line, we know if the contract, if the address given is a contract or not. Next line is we are able to send money to this recipient through the low-level function call. So this is the recipient, which is the recipient of the Ethereum, and then we call, and then we put the money over here. This is a little bit in syntax, a little bit interesting. So you need to have a curly bracket over here. Then you need to this attribute value pair to show that you are going to send this value along with your function call. And then the argument of function in this case is no argument. Okay, no level. So this was actually calling no function at all. It's just going to send the money to the recipient. The next one is function call. So as you can imagine, you're going to be calling the function. And which function to call and what is the argument, they are all encoded in the data, which is a sequence of bytes. Okay, and then the other side is going to decode it. Okay, so the encoding is going to encode a function name, signature, and all the arguments. So that's function call with value. In this case, value is 0, so that means we are not going to send any money. We just simply call a target function and argument encoded over here. Okay. And then it's going to return a sequence of bytes, which is it's called call data. So we'll encode the return arguments. And the function call simply is a wrapper for function call with value. Okay, this one doesn't send any money, so this is why it's encoded 0 over here. So let's look at a function call with value, which is function call with value is target, data, and a value. So in this case, we are assuming, let's say value might not be 0. Then we are going to call the target, the data, and the value, and the address. So these two, the only difference between these two is we add a fourth last argument over here, which is the error message. Okay, so that's you can customize what error message you want to do. So this is the error message encoded. So this one function call with value, we have target, data, value, and error message. You can customize your error message over here. First of all, we're going to check if we indeed have this amount of money received. In other words, does the contract sender have this enough balance to send this amount of money? But otherwise, you are just signing an empty check, right? So we have enough balance to send the money, and then we are going to send the money right here. So what we do is we call the target, which is the target contract, and then we call using low-level call, and then the function name and also argument are encoding the data, and then here's the money we send over. And then after we call, we are going to check the returning. So all the return will return in two variables. One is the return code, is it true or false, successful or not successful. And the other one, return data, usually encode, for example, the value, including error value, including normal value, such as what is the balance? Then it's going to return a number, right? So on, okay? So let's look at what verify call result from target look like. Also 4 arguments over here. First one is what target address we are calling. Is it successful or not? Over here, Boolean variable. Return data, encoding the return value, either successful value like a balance or unsuccessful error message from the contract, the error message returned from contract. And this one is customized error message that we as input. So we just pass it along to here. Okay. We also have function static call. Everything's the same except function static call does not allow, when we call the target function, does not allow the target function is going to change any state variable. In other words, blockchain cannot be changed. So it's a protection, a more careful call. Everything else similar, except it's called static. Again, not allowed to change the state variable. But in any case, we use the same verify call result from target, trying to verify the result. Another one is called function deleted call. Everything's the same except deleted call is going to be using the same MSG value and using the same address. In other words, the context is not going to be changing. We're still going to be stick within the same contract, within the same message value. We're going to talk about deleted call later in more detail. It's going to be a very important topic for security by itself. So we're going to, probably have one class for this, just for deleted call later. Okay. So this is low-level function deleted call. Again, we are going to verify result from target. So it's time now to look at the function, how we are going to verify call result from target. First of all, if it's a success, that means the return data is going to encode the value returned by the function. So what we do is we need to require, in this case, that the return data should either equal to 0 or not. If it's equal to 0, that's a little bit interesting because it's successful. So that means probably don't expect the function return any value at all. So it's going to say, is it a contract? So this is very careful check, because if you call a non-contract, you are still going to return success. So that's a little bit surprise for most people. But it's true, unfortunately. So when you call a contract and that contract doesn't exist, unfortunately, you call a non-existing contract, any function you call, success is going to be true. And then return length is also going to be 0. So that's one thing we have to be very careful when we're doing a security check. What about if I call 0 edges? What about if I call even arbitrary edges, an arbitrary function there, and that contract actually is not even valid? What's going to be returned? Well, it's going to be return success and length equal to 0. So this is why we have to add this line to double check. Okay, and is it a contract? If it's not a contract, then we can defer. Else, we're going to return the return data, which the client can decode what's in the return argument. Otherwise, if it's not successful, we simply going to return revert. So simply we are going to revert. All right. So it's very important for a function call to be successful based on 2 conditions. Number 1, it's a success. Number 2, either the return data length is 0, then it's a failure, or return length is not equal to 0. So in other words, the successful part is going to be success, and return length is going to be if it's equal to 0. Okay, so that's two cases. Let me analyze it a little bit more. If it's equal to 0, that means I need to check if it's a contract. But if it's not equal to 0, I don't need to check because there are already some data returned. So it must be a contract. Okay, so I think that's the 2 cases. Even when it's successful, we have to analyze 2 cases. So don't interpret success is a success. Success could be still 50%, could be still a failure if it's not a contract. Okay, so here we have another verify call result. Let's see. And this one is if it's success, we return data. Otherwise, we fail. So this one we didn't check the return data length. So that means we have to be very careful when we use this one. Okay, so this is the older one, which is not that secure. Try to use this one if possible. Okay, because this one is just for, I think, for backward compatibility, but I didn't check if the return contract is and I didn't check if the result is actually returned from a contract or not. And then finally, we have the revert, which give you the return data and the error message over here, which is using assembly language over here. First of all, we are checking if the return data length is greater than 0. Then we do this. Otherwise, we have to use the customer message, which is from the input over here, because the target probably the return data length is equal to 0. So we have to use our customized error message. Otherwise, we can use the error message returned by the contract. So over here, we assign the size of the error message. In this case, return data is a byte. So the first word, which is the 32 bytes, will contain the size of the array. So we return the return size over here. And then we are going to revert from the error message. And this one is the offset of the error message. Remember, the first word is the size of the return data. So we have to add a 32 to skip that first word. And then this is the size of the error message, which is return data size. So that cover our discussion of the address, and then come back to here. So where it could be the problem? Well, I think it's very hard to break this line, of course, because you are calling token balance of, no problem. Same for this, no problem. Of course, no problem. I don't see any problem over here. You transfer money from yourself to the borrower. So the only thing is this, because as I said, it's a little bit dangerous to let a flash loan call arbitrary address. They don't know what address you're calling, and then arbitrary function call. So what about if this target is a fishy contract, that it's a malicious contract that the attacker created? So that means you are going to call a malicious contract and a malicious uh, function. So the question for you is, how can you create that malicious, bad contract and bad function, so that by calling that function, you are able to steal the money from the flash loan. And again, it's a little bit tricky because 34 is a protection over here, and 29 is a protection over here. So how can you break both of them and be able to steal the money from the pool? But good luck. We will talk about this solution on Thursday.